Hello, everyone. Welcome to this week's binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Today we have some cool notes on ASAN to cover, an OpenSSH double free, and a PS2 Vuln that can hack PS4s and PS5s, and some other various topics mixed in there. And we'll get into all of that after Z gets into this week's Spot the Vuln. And also, thank you, Adam J. Leck, for the T1 sub. Appreciate it. All right, so Z, I'll let you get into the Spot the Vuln, and then we'll get into some of our topics.
All right. This week's Spot the Vuln was a kind of a constant define issue in C. See it from time to time. Really, one of the best practices when using a define in C is always kind of wrap whatever you're including in brackets. Main reason for that is just, when you drop something in, the way these defines end up working, it's almost like text processing. It looks for the word, in this case, we have a few defines like word size, max buff size, and padding. It just looks for that word and drops in whatever you wanted there. Literally just dropping it in there as is. And so the problem here is in this copy data function, presumably attacker controls data len. What'll end up happening is it does this if data len is less than, and now using those defines max buff size minus padding minus 1. What'll happen there is that will become the max buff size, which is 256. So 256 minus 1, and then padding is 1 plus word size times 2, word size being 16. So I'm just going to plug that in there. This kind of resolves down to being a 256 minus 1 plus 16 times 2. And given the precedent system, at least I tested this on Clang, I believe GCC does the same thing. Like, they'll resolve that multiplications before they actually go on to do the left to right addition. And I believe they'll do multiplication left to right. So largely like what you were taught in school in terms of like PEDMOS or whatever you want to say, following that sort of precedence with it. I feel like that's something that's in the C spec that I probably should have looked up to double check on exactly where it happens. This is just one example though, but what ends up happening here is because of that multiplication happening, and this isn't being grouped into like into brackets telling it to, resolve everything here first, it becomes max size minus 1 plus 32 minus 1, which is not really what they're trying to do. Basically max size plus 30, which is ideally they're trying to subtract padding rather than adding it. So it kind of just messes it up when they end up dropping those defines in there, and the data length check just isn't valid when they're doing the allocation of max buff size. Doing a comparison that technically adds to it just isn't accurate. It is something that's really easy to gloss over when you're reading the code. It stands out more if you're actually doing like the disassembly because you don't see the constants in there or the defines. But yeah, this is definitely one of those bugs that just pops up when people misuse the defines, and it is really easy to overlook this one. Unless you're looking directly for it, you'll just think, oh, padding's this size, and like you think about the end value rather than kind of the text processing that happens during this.
And it's a bit more of a mathy problem too than some of the other spot the vulns that we get into. So you kind of have to work through it to understand what the problem is and how it's useful to you. So
well, it's a common enough like vulnerable pattern. Like it's not like the core issue is the fact that you're not wrapping padding in brackets. Like that would be a best practice. That is the thing I would kind of notice if I was seeing these defines and see any sort of complex define that doesn't use brackets. It's like, well, where is that getting dropped in? How can that mess things up?
all right, so with that out of the way, we'll get into our first topic, which is a pretty cool post that was put out by Londare. So yeah, I saw this one post on Twitter. It was pretty cool. Its main premise is improving ASAN on C++ targets. So yeah, this serves as both like an opportunity to talk a little bit about ASAN and some of the cool tricks here. So for those not too familiar with ASAN, stands for address sanitization, and it's very useful for things like fuzzing and just exploit debugging in general, as it'll instrument code to try to cause crashes on corruptions that wouldn't normally cause a crash. So things like use after free, out of bounds access, etc. It might not be critical enough to cause a crash in that moment, but ASAN, the idea is it tries to catch it. And it does that by adding instructions around all memory accesses to check a shadow mapping that keeps track of the memory states. So if you try to say access a memory that's been marked as invalid in the shadow map because it's been freed, it'll induce a crash and provide register state and stack trace and stuff like that. But of course, it's not perfect, especially when you get into C++ with things like container objects. It's a lot harder for ASAN to do a good job there because C++ containers in the standard library, for example, like string, are pretty convoluted actually in how they work. And there's a lot going on under the hood, which you might not expect because a lot of it is abstracted away from you if you're just using it as a developer. But internally, it does its own size tracking. It does like reallocating for larger containers and stuff like that. There's a lot of memory management stuff going on under the hood. And the same thing for other containers like vectors. But it turns out that LLVM's libc++ actually has some ASAN enlightenment, as they call it, for vectors to try to catch these sorts of problems. So, like an out-of-bounds access and a vector, for example. And it'll do like some annotations and try to catch that. But in order to get that, you have to use like LLVM's libc++. It's not something that, like, I don't think that's in GCC's C++ standard library implementation. Now, strings and such don't actually have this, but you can implement it because Google's ASAN allows you to manually poison memory, so you can kind of roll your own extended instrumentation on top of it. So the post goes into a little bit about how you can do that, either by doing it the proper way, like actually adding the instrumentation into string, or just kind of hacking strings to copy it into a vector and have the vector instrumentation do all the heavy lifting for you. But yeah, I mean, there's a lot of cool information here, both about how ASAN works and um, how you could potentially extend it for your own use. There's also some miscellaneous other tips and tricks in here, like shouting out the sanitize recover argument to try to allow the application to continue after finding a crash. Not only can that help you keep your throughput up for something like fuzzing, but it could also allow you to find more interesting behaviors that would happen after a SAN catches the bug.
Yeah,
So yeah, I mean, there's just a lot of cool tricks in here.
that I think is kind of the big thing with using recover is it does give you that opportunity to not only see what the initial vulnerability was that ASAN picked up, but where does it go? What else could happen? Because it is sometimes easy to dismiss certain ASAN reports where they don't look that useful, but had it kept running a little bit, it actually does kind of pick up to a much more serious corruption rather than just crashing on the first corruption that's seen. Something definitely to keep in mind when doing a fuzzing campaign.
Yeah. But like the main thing this post tries to do is highlight like ASAN is very cool, it's very useful, but it does have some weaknesses, and here's some things you could do to potentially address them. I think towards the end, it also talks a little bit about Rust. And the fact that it doesn't have any ASAN enlightenment, so that could be an area that could be worked on as well. And that kind of ties in well to our next topic because our next topic is about Rustproofing the Linux kernel and talks about memory safety issues in the kernel, even if you're using Rust for your driver. So yeah, I guess we'll just segue right into that. Z, I know you found this one interesting, so I'll let you get into it.
Yeah, I thought this is kind of interesting post and something we've talked about a handful of times as we've talked about Rust being implemented into or being supported in the Linux kernel and seeing things start to actually use Rust in the Linux kernel. What does that mean for security? Is Rust going to get rid of all the vulnerabilities? And I thought this was a really awesome post. They've actually got 4 parts coming. They put out 2 parts of it. First part is about information disclosure, like pointer leak. And the second part is kind of race conditions. But what they're doing with these posts is they're looking at, as Linux developers or driver developers for Linux are taking like their old C drivers and porting code into Rust. What are kind of the patterns that they're going to be thinking about? How are they going to be writing that code? And what type of mistakes are they likely to still be make, or what type of mistakes could still be made in Rust? Um, even though Rust deals with a lot of issues, one of the side effects here of being in the kernel especially is that they do have to use unsafe code. Anytime they're going to be writing to a specific pointer and they're grabbing like the pointer for like userland data read or something, or just they want to write to a specific kernel pointer, using those raw pointers is an unsafe operation. And unsafe is like anything that happens in there just lets it all happen. You don't really specify, well, this is unsafe in this way, but not, and still do all the other checks or something. Like when you write unsafe, it's all unsafe. So you can have kind of unexpected bugs show up where they're doing their bounds checking, for example, and you can still kind of have a race condition happen where somewhere else is accessing or had accessed that same buffer, even though normally inside of Rust you can't really have that. Using the unsafe, you kind of open up some of these issues. One of the interesting ones they do call out is the mutex aspect, where somebody might write their code here they'll create the mutex for their driver, and then they'll call into that mutex, lock it, and implicitly the way the mutex here works is when the mutex goes out of scope, it's automatically unlocked. So they only make the state mutable.lock call and access the buff size value, and it gets unlocked just when this whole variable goes out of scope. They don't actually need to call the explicit unlocking of it. They also call the same lock a little bit further down. But that pattern, like, if somebody were to write this code, they would think they're locking the thing there. And so between these two uses, basically, as soon as this if line goes out of scope, so as soon as it's done executing and it leaves and goes on, it's unlocked during this period. I know that's blank lines right now, but it is unlocked. So you still have the race condition, even though you might expect, because you're doing the locking, that you wouldn't. So just like, it's a fuck gun with the mutex. It's something that, like, somebody who's aware of how Rust works, how the locks work, shouldn't make this sort of issue, but they could make this sort of issue, especially if they're looking at their old code and kind of porting it, like for like, rather than thinking more about the Rust idioms. Although they do go into showing a bit about how even, you apply these Rust idioms and you still end up with various issues. They kind of go through this, make it more and more rusty, and still and when I say rusty, I mean like the Rust idioms. But they just end up showing these other ways that it gets broken. A lot of them come down, the semantics of actually locking, how you should do that. And what I thought was interesting about both of the posts that I've read here, so first part again was both the info disclosure, and the second part is more about the mutex stuff, or largely about that, and just race conditions. Really just comes down to the fact that there are still going to be bugs even as people are writing in Rust. I believe Killtop09 mentions there, unsafe equals there be dragons. And yeah, that is such a key thing when it comes to Rust. It's not that Rust is perfect, because it's not. But when it comes to auditing Rust, there has been, as far as I'm aware, only one memory corruption vulnerability in Rust that did not involve unsafe code. The general pattern for memory corruptions in Rust is either an unsafe code will break the assumption that safe code makes later on, or safe code will, or unsafe will just break the assumptions of the safe code before it. Effectively, like, assumptions are getting broken somewhere and it involves the safe code on one end or the other. And what doesn't end up happening is just safe, what would be referred to as a safe to safe memory corruption. So having that unsafe just makes it a little bit easier to start auditing this and look at, is this unsafe code correct and doing what it should be? And in the first post, they actually call out a kind of interesting trick or issue with just trying to audit the unsafes. So first of all, the first one here, they also talk about the fact that you can have information leakage through the padding in structures. So if structures are not, if they're not packed, you can have some padding that can leak data. Even if it's initialized, the values get initialized, the padding does not. So you have to zero initialize the whole thing. Otherwise, you leak kind of the risk there. And that can happen in Rust. And there are some Rust patterns implementing one of the, I forget exactly what the trait was, but implementing one of the traits, there's a chance, they could be leaking it there. So, just more places that you could still see vulnerabilities in the Rust code. They call out, though, that this P in print K, when you give it the P format specifier, normally in C, that will print out like a hashed pointer rather than the actual thing, and you have to use PX. One of the problems on the Rust port is the Rust port just prints the pointers if you do that. Does depend
Oh,
on
that's
codecs.
interesting. I never knew that.
That the Rust just printed the whole pointer or that did the hashing.
That it would print the pointer, like that it wouldn't respect the pointer censoring
Uh,
rules. That's interesting.
yeah, I believe they mentioned that they're like that's getting fixed. That's not going to stay the case. I might need to double check that. Say they had a couple things here. The other one, the reason I actually initially brought this post up is that let's see here. I'm just scrolling through. I find basically they found a way to include unsafe code without actually using the words unsafe in their code through this PR info macro. The key thing that happens here is you have PR info. It's a macro. You've got the little exclamation point to indicate that. It takes its input and it has an implicit unsafe inside of the macro itself. So the device driver, whatever, they're just going to write PR info, and they're not going to realize that this write raw is necessarily unsafe or in an unsafe group. So you can kind of hide the unsafe code there and not notice. That said, this is another thing that is definitely getting patched. A fix is due to be merged with the next release for that, so wouldn't look forward to being able to abuse that too quickly. But it's still interesting that like you can kind of obscure where the unsafe exists. So you might look at pure info and look like, well, is it using unsafe correctly? Auditing the unsafes. And it's a lot harder to audit because it's going to be dependent on everything using that macro. So again, just more places that you can have these bugs show up, which is what I thought was really interesting about these posts. They are using a intentionally vulnerable driver to kind of show this and start off with certain bugs and demonstrate that. So it's not like they're using real bugs, but they are really trying to get inside the head of a developer who's going to be porting and trying to bring their code over to C and the sorts of issues that they might be unaware of when they actually do that. So I thought it was an interesting post just for showcasing that aspect and the fact that you can still write these memory corruption bugs in Rust. It just makes it
Yeah,
a lot harder.
yeah, they are a bit contrived, but it does a good job of demonstrating what they're talking about.
The specific
Um,
examples are contrived, but at the same time, like I don't think it's that contrived when they're talking about how the developer might be thinking about reporting their code and
no,
doing especially that like for like, line for line sort of translation of I did this in C, therefore I do this in Rust. And that just creates problems.
yeah, and the other thing is like it might seem obvious that code and unsafe is potentially unsafe and can cause safety issues. But the thing that's notable is especially when you're talking about kernel, there are like a good number of operations that pretty much require you to use unsafe. One example that I'm thinking of, and this might not be the case anymore. I know it was at one point. But things like linked lists, you can't actually implement like a doubly linked list without using unsafe in Rust, or at least you couldn't at one point in time. Like I said, I think that discussion was like a year ago that I remember that being brought up in. It might have been addressed since then. Like Rust might have a better mechanism for that now, but yeah, I mean, there's a lot of stuff in kernel that's going to require you to do things that the burrow checker isn't going to like. So unsafe is kind of a necessary evil, even when you're trying to roll in the more memory safe languages into the kernel. So like things like this are definitely like it's not like a driver written in Rust is not going to have any memory safety issues guaranteed. It's still possible and even easy in some cases to have those types of issues, because kernel is just it's kind of a difficult beast to do correctly, and there's a lot of special considerations you have to have. So yeah, I think this is a cool series of posts. There are a few other parts that haven't come out yet, um, or at least they haven't last I looked. I don't know if you double checked today, Z,
I
to
didn't
see if part 3 came out.
check today, but yeah, they've got a part 3 for integer overflows, which actually exists. Most languages allow you to kind of get integer overflows and shared memories. Another, that's going to be part 4. Seems like they
Yeah,
have these written, they're just releasing them slowly.
shared memory in particular, I think will be like pretty interesting. So maybe we'll cover it again when that's put out. But yeah, because shared memory again kind of falls in that classification where it's like it's a necessary evil. It's very performant, but it's also super hard to do correctly.
Oh,
So,
part 3 came out today.
oh, there
So
you go.
we haven't
So
yet covered it, but it is there if you want to check it out.
yeah. But yeah, like you said, it covers some interesting cases and some good cases to be aware of, especially as Rust starts to make its way into more and more of the kernel. Which, over the next few years, we'll probably see a decent amount of the more sensitive and exposed drivers being converted over. So yeah.
Yeah. Killtop09 also mentions we have weak pointers in Rust, which can be used to implement doubly linked lists. So sounds like that's not an issue. That said, I mean, as I understand it, a lot of those lower level objects do eventually have like some unsafe used within them. Like even common libraries, like unsafe is used a lot. And unsafe isn't bad. Like it's not that you need to avoid all unsafe. The key thing that Rust does is it marks unsafe code as unsafe, so it can actually be audited rather than everything being potentially unsafe. So, it's still a net positive to use. I think some people kind of look at, well, if there's unsafe, it's just inherently dangerous, and it's more just marking. Like, at least in my mind, the big value is being able to mark and isolate those areas to see what are the consequences of what it's doing there and what makes assumptions that might break on that. We actually, Spectre, do you remember what episode we actually covered that we did a research paper about a bunch of Rust issues?
I remember the paper. I don't remember which episode we did it on. I'd have to like search through my notes to find that out.
Yeah,
Which
because
maybe I'll do actually when we get into the next topic. I'll take a quick look, just see if I can find it.
yeah, I'm taking a look just right now to see if I can find it. Because yeah, we've definitely talked about this sort of thing before, where unsafe code can introduce issues. We did have kind of our last main kind of rusty episode was when we had Bastian Gruber on with his book. That was back on episode 99, but I think I brought up that post at that time, but I did not. Doesn't look like I have a link in our show notes to when we actually talked about the paper I'm thinking about. I'll see if I can add it at least to our show notes before they go up tomorrow.
All right, cool. So yeah, getting into some vulnerabilities, we have an SSH OpenSSH pre-auth double free vuln that was patched in version 9.2 P1, and of course, where it's pre-auth, it's been garnering a good bit of attention. And yeah, Z will get into this one.
Yeah, and it is just double free, reasonably straightforward when it comes down to it. The core issue, or at least the original issue here, comes down to this compact hex proposal. Basically, what ends up happening in here is this gets passed in. Um, I've got that just as RP, but I can't remember what that was now. The options.key algorithms, or kex algorithms, sorry. Key exchange algorithms, gets passed in the character pointer there, and there's this one flow where in compat, if it has the SSH old DHGX flag set, it'll clone the pointer, goes through whatever, and then it frees it. So that is just like, CP equals P. So just copying that pointer, frees it, ultimately just returns it again anyhow. And then of course later on, where it's actually supposed to be freed, off when it is basically there's the assemble macro. It's basically just assembling all of the hex algorithms that can use it, frees it there, also creating this double free situation. I believe all of the crash examples basically just take advantage of the fact that malloc doesn't like it when you free the same pointer twice in a row, so it'll crash there. In terms of exploiting this, the way you'd actually want, I believe I'm wrong about that actually, because I think JFrog mentions it being on a write.
Because I was about to mention with the double free aspect, that is a little bit flimsy because the way that the allocator detects that is it just checks like, is the last pointer that was freed the same as this pointer?
Yeah.
So if you have any like allocations or frees in between, it can't do that detection. So
Yeah, it doesn't run through the whole list to see if you've ever freed this before. It catches those cases though where you have like a really quick free and then a free again, which is a fair number of double free cases. So it does catch them. In this case, they were able to get around that by they have the free, they spam something else, whatever, to get it allocated again immediately. So now when it gets free that second time, it's already been captured once, and they kind of have a use after free with the other thing that they've got. Or at least so Qualys did. Qualys was the original group to report. They had an update put out yesterday about this, where they mentioned they were able to get RIP control through this use after free. So at that point, I would say this is very likely to be exploited. I kind of disagree with JFrog when they talk about towards the end here. They basically mentioned that according to a recent update, Qualys Security has managed to leverage the double free for a limited remote code execution exploit, which is true. That's effectively what they did. They got it to RIP control, which is a strong indication of getting that. But they kind of called out as when no memory exploitation mitigations are applied, which again is true in terms of what they actually managed right here. But I would not want to set that as like a restriction on, like, you have a double free, and it's like they're more stating that they gave the severity because it's only when there's no memory exploitation mitigations. Realistically, I'd have to believe that with a double free, they should be able to turn that into a read at some point to leak at least some bits of data. They are restricted, so that is maybe an important thing to note. This is happening kind of inside of the Pre-Auth sandbox, which varies depending on what system you're going on. Maybe like a seccomp filter. They have a few different implementations, seccomp being one, systrace being another to limit your syscalls. They have like a capsicum option, or have like a really simple sandbox, just R limit. So it does depend a little bit on how strong the sandboxing is. But since they're in that sort of sandbox, they are limited in terms of what actions they can get to happen in there. Like, there are some definite limitations, but double frees usually are able to grant some pretty powerful primitives when you can match up the right objects. Within some more complex software, they're lowering the complexity because being inside of their sandbox, being off inside of that little forked off area, definitely a limitation. I'd
So there
want to
is
assume
one.
that this is just going to be exploitable and they can turn this into an info leak at the very least. Qualys specifically calls out roping as an option. So calling out NX as being one of the things, like no mitigations like ASLR NX, just doesn't feel accurate to me. I believe
Okay,
they
no
do.
execute isn't a huge thing, but ASLR kind of is.
ASLR is usually that's just, finding another bug, or again, in the case of double free, like that can quite often be turned into another read.
So I think there's
Again,
one aspect that you're kind of you've ignored covering, which I think is relevant, and that is the fact that with double freeze, like, you're effectively able to cause like a targeted use after free with a double free, and something critical with exploiting use after freeze is you need some kind of heap rate reallocation gadget that's accessible to you pre-auth. So Qualys seemed like they were able to find one for getting RIP control, which is pretty cool. But your heap allocation, like reallocation gadgets, are going to play a big part in what you can actually do with it. And where it's pre-auth, like, your options are going to be very limited there, which you kind of touched on. But yeah, I mean, not only are you limited on what channels you have for exfilling data, but you're also limited on what kinds of data you can reallocate into a freed slot. So it is like a little bit of a mitigating factor there. That
it
said,
definitely
like,
is. But
like,
go ahead.
ASLR does matter a lot on remote targets as well. But I did want to comment that because this is in a forked daemon, like, you're not crashing. Like, if you try to exploit this bug and you fail and you crash or something, you're not going to be crashing the entire server. You're just crashing the daemon that was spawned for your connection. Because of that, you're not really like it's not really like a one-shot exploit, and it's like if you fail, you're screwed. You can continually try to do this. It might be noisy, like you could end up setting off logging or whatever, but you could keep trying again and again. And especially if it's running in a 32-bit address space, you could effectively brute force the ASLR and get like one attempt that ends up working. So I kind of disagree with the pessimism of JFrog on the exploitability of this, but where it's remote, the ASLR and stuff is like worth calling out as limitation still.
Yeah, and I don't disagree with you. I guess my take is more towards the aspect of not defaulting to it being unexploitable. Which is what I feel JFrog's kind of doing, is they're defaulting on they haven't proven it exploitable, therefore it isn't. Whereas my take is more, I'd feel, like there's a good chance that it is exploitable. But you're absolutely correct in calling out like there are these limitations, and actually the sandboxing is a big thing. It happens pretty early. Um, it's happening during like the establishment of some of the crypto. So very early on in that chain, you are going to have very limited. It's not like you're interacting with the process to, like a kernel heaps array or somewhere you can keep calling the one syscall over and over. Like you don't really have that here, and you don't have because it's forked. You're not having other clients being able to impact. So you can't like open another connection, do anything there. So huge limitations on that. So it very well may not be exploitable. It's just in the absence of that evidence, a double free feels like something I would want to lean towards saying will be found to be exploitable. Somebody will come with a trick for it rather than taking the assumption that it won't. But you're totally right. There are a bunch of things that make this one a little bit more challenging in particular.
I feel like that aspect of it being a fork process that's specific to your connection is very interesting, because it's like a two-bladed knife. Like it provides both benefits and like downsides. The benefit is, you can keep trying it. Crashing it isn't going to deny like DOS the entire OpenSSH service. But on the other hand, it also limits your influence over the heap and stuff. So yeah, it's a very interesting like wrench to throw in there with how the exploitability is.
Yeah, the exploitability is interesting here. Qualys has had some real, like, their pseudo bugs had some interesting exploits, so sounds like they're still kind of working on it, given that they did just release the fact they got the RIP control yesterday. Uh, so I'm kind of hopeful they might find a way to exploit, and we'll actually have a cool exploit out of it.
That'd be cool for
Even
sure.
if they do get the RC, like they are in that sandbox, which likely, not necessarily in all cases, like I mentioned, the R limit sandbox is pretty minimal. But setcom and stuff. I was taking a look at some of the code there, like it really does cut down on what you could do to escape, because that's kernel enforcing that sandbox. That'll be another limitation here. Even once they
Yeah.
do get RIP control, like you'd have to have a kernel bug in a pretty limited subset of calls. There's nothing really exotic in the set that I saw being allowed.
Yeah. And taking something out of chat, Current Exploit asked, what's the difference between OpenSSH and OpenSSL? They're kind of tackling different tasks. OpenSSH actually relies on OpenSSL, as far as I know, for doing the crypto stuff. OpenSSL is more of like implementing crypto functionality for SSL and TLS and stuff like that. Um, OpenSSH is more for just the SSH protocol in particular. So it's not as broad. Like it's not going to have as many things depending on it. Generally, it's more of just like here's something for doing SSH. They're kind of tackling different tasks, but there is some cooperation between the two projects, because yeah, like SSH is obviously going to be using crypto fairly heavily for doing authentication and key exchange and stuff like that. So yeah, there is a relationship there, but they are like aimed at different goals.
Yeah, I think the main thing that OpenSSH, like where it's being used by and large, is just SSHD, running an SSH
Yeah.
server. Whereas OpenSSL tends to be adopted into a ton of other libraries or
Yeah, a lot more
programs.
adoption.
Yeah.
Yeah. All right, so for our last topic, we have part two of a three-part blog series on mast1c0re, which is a PS2 exploit chain that can achieve arbitrary code execution on PS4 and PS5 through the PS2 emulation support. This is all focused on save game-based exploits on Okage Shadow King, which had a stack overflow in the player or town name, which I'll note that while PS4 and PS5 saves have some crypto layers and such on them, PS2 ones don't, which is partially why they're a more viable attack surface here. You don't really see too many like save game based exploits on modern consoles nowadays, but this is kind of an exception to that rule. So yeah, part one was mostly talking about modifying save games and extracting it and whatnot. More of the background on building tooling around modifying the save games. I won't really cover it too much here, but you can check it out if you're more interested on that side. Part two covers the save game vuln and exploiting it. And part three, which isn't actually out yet, at least as of yesterday, I didn't check today, covers exploiting a bug in the PS2 emulator to escape it and be able to get like full userland code execution. So yeah, starting off with the bug, they noticed that the profile name was at this particular offset, hex 850 in the save game file. And aside from a checksum, it's mostly unprotected. So they did need to deal with the checksum, but besides that, they could set it to whatever they wanted. And yeah, it's a very straightforward overflow. By just providing like a very large string there, like say 400 bytes, you could overflow a stack buffer that profile name was copied into and attack the return address on the stack. And yeah, so honestly, it really isn't that interesting. Um, it is in MIPS, which is maybe a little bit of an interesting aspect of it. One thing I thought was cool was how they debugged the exploit actually, and for that they used PCSX2, which is like a PS2 emulator. They used the debugger from that, created the cyclic pattern payload, and then used PCX2 to build their payload and debug it. Furthermore, since PS2 didn't have like ASLR or no execute or anything like that, you could do a typical shellcode attack, and that would be in MIPS since that's what the PS2 ran. After that, they basically do some fix up and write a loader that'll run a payload from the memory card and even put in a basic elf loader. Like I said, the bug and the exploit aren't too interesting, but the debugging method and the fact that it's MIPS stands out a little bit from some of the other topics that we typically cover, or don't cover due to the bug being a bit more simplistic. And on top of that, for many reasons, this is a great exploit vector, especially for the PS5, which is something Cturt mentioned in his original blog post, actually. And there's multiple reasons for that. One of them is the fact that the PS2 is one of the only features or the PS2 emulation, I should say, is one of the only features on the PS5 that has JIT capability for running code, which is extremely useful for exploitation because, especially on the PS5 employs execute-only memory or exotext regions. So doing things like ropping are a lot more difficult because you can't really get gadgets. Because as soon as you try to read or dump code sections, you crash. Um, the impact is also pretty high here because this could be used for running pirated PS2 games, which Sony does have as their highest tier of PlayStation Now, selling as a main feature, is that ability to play different PS2 games and such. Um, Also, on top of that, because this PS2 stuff is all bundled like per game, it's also very difficult for Sony to fix because it falls far out of their scope. Um, because they would have to track down like every PS2 game and issue fixes to all of them, and it's not really centralized. So yeah, even though the bug and the exploit here is pretty straightforward, they're not really doing any crazy chaining to get around mitigations or anything like that. The impact here is pretty high in the console space. So for that reason, it is an interesting post and an interesting exploit chain. I think part three will be the most interesting when they talk about escaping the emulator. Sadly, that's not out yet, so maybe we'll cover that when that comes out. I'm not sure when that's planned to come out, but yeah. Mainly, what's interesting here is the aspect and the future research potential built off of like the mast1c0re exploit chain. Um, but yeah, like I said, not too much in terms of the bug. It's a pretty straightforward MIPS Stack Overflow. Um, though I know like MIPS in a way is interesting in and of itself because you were talking a little bit about this to me the other day, Z, where it has like delay slots and stuff. There is some cool stuff you can do in MIPS
It
that you don't
has
really see in
some,
other architectures.
yeah, I mean, it has some unique traits, I guess. But when it comes to exploitation, like it doesn't make that much of a difference. You're doing your shellcode for whatever you want. We do have the one question in chat. Airfrischung. I probably did not get that correct, but I don't understand where the executable code comes from after loading the faulty save game. It's basically similar to just your traditional Stack Overflow, where you overflow the stack, and in doing so, you overwrite the saved return address. So as soon as that function returns, it loads the return address that you wrote onto the stack and jumps wherever you want in the code, including to your own payload or your own shell code of whatever you want to execute. So as for where it comes from, you're including what like the payload you want in the save game. Spectre, as you were talking about like the debugging and stuff, I will say PCSX2 does have a really nice debugger built in. I still wish they had a decent GDB stub, just because I would prefer to do that. But like its built-in debugger isn't terrible, and properly or largely supports like the motion engine stuff, and some things that trying to get into GDB is just a bit of a pain.
Yeah. Current exploit mentioned, I wonder if they can get a HackerOne bounty. So I believe that's touched on briefly, maybe in part one. Basically, I think there was one HackerOne bounty issued, but Sony won't be issuing more because it's kind of out of scope. It's not really their code, right? Like this is an issue in PS2 games, and they kind of just have to deal with the fact that PS2 games aren't going to have the memory protections and stuff like that. It's not something they can really easily address. So it kind of falls out of scope of their bounty program. So yeah, it's kind of an interesting area, and it will be like a future, research. Like it will provide opportunities for future research on basically any firmware on PS4 and PS5. So yeah, the implications are pretty cool here.
Yeah,
Like
I
I
thought
said,
the
hopefully we'll cover
implication
the emulation escape when that comes out.
I thought the implication was interesting as you're talking about like using it to then launch your attack against PS4, PS5.
Yeah.
Yeah, having JIT is like a huge advantage. And I was really surprised when you mentioned that basically this what like the emulator itself wasn't just like a library they could update, but was kind of packed in with every single game or all of like the PS2 games. Kind of surprising that they went that route. I'm not sure if that's so like the developers of the specific PS2 game could then turn around and like fix up the emulator if necessary. Um Feels like that would be asking a lot of the PS2 devs who may or may not still be around in some of those cases. I don't know what the deal is with getting your game on PS Now. But definitely a surprising choice to not use like just the standard library that could be updated for that.
It's a weird situation for sure. Um, I can't really rationalize it either. It's kind of weird, but yeah, that's the way that they went, and now they just kind of have to deal with that. All right. But yeah, that's basically all of the topics that we have for today. So unless you have any last minute thoughts, see, we'll wrap it up.
I just had the one shout out for this week, which kind of ties in with our first topic actually about ASAN. We were talking about ASAN, some things there. There was a post that came out a couple weeks ago all about UBSAN, Undefined Behavior Sanitizer. Um, Goes into a lot about how it works, how you can use it, some of the different options and stuff. Um, UBSAN is it can catch a lot of issues that aren't strictly speaking going to be exploitable, but may be exploitable. It's an interesting sanitizer that can find a lot, but kind of because of that has a lot of noise to wade through in some software. Really depends on what you're running and stuff, but worth taking a look at if you're going to look at using sanitizers in your fuzzing. UBSAN is just another tool to take a look at.
Yeah, and I will say, like, undefined behavior, it's kind of a weird class of bugs because it's not as obvious what the immediate impact could be, but you could have some very subtle bugs created by it because compilers take advantage of UB to do like a lot of optimization type stuff. So it can cause some really subtle bugs, but like you said, there is also a lot of UB in regular software that just doesn't cause any security issues, and it's a lot of like the signal to noise ratio kind of sucks on it compared to other sanitizers, but it still might be useful in some cases.
Yeah, at
So
least when you're running all of the UBSAN, you can run different like specific sanitizers from it. So like it has several that are like integer sign changes or integer truncation or things that can pick up their integer overflows, of course. Like those are things that are likely to be able to introduce bugs, not necessarily security bugs, but they might. So you can just kind of detect those and raise a warning. UBSAN is one of the things that I would recommend. Uh, Not letting it crash the program whenever you run into one of them, but just capturing the fact that the crash did happen at least.
Hmm.
But yeah, there's a lot, and you can actually see the list here on screen. There's quite a few tests that it can look for.
All right. So that's all the topics that we have for this week. As always, thanks to everyone who tuned in. If you want to check out past episodes, you can find recent ones on Twitch and all of them on YouTube, Spotify, Apple Podcasts, and more. Also, if you want to join the community and check out the Spot the Vuln channel on our Discord, Discord link is down below and or in the chat, and you can also follow us on Twitter for announcements for when we're going live and such. And yeah, we'll see you next week.